Okay, hello everybody. Welcome to the presentation of transport phenomenon. And here's the title of our group, which is called General Club Poroelastic. And here's the list of our team members. So I want to start with what is porous media. So porous media refers to the material that contain a network of interconnected pores or valley space within a solid mixture. So this pore can be filled with the flow like air, water, or oil, and it allows substance to move through the material. So in our life, the kitchen sponge, filter paper, soil, and even human skin will be counted as a porous media. So the application of porous media is very important because it is used in many industries, such as the extraction of groundwater, oil, natural gas, and which are highly mutual industries. So as the research on porous media is going deeper, so the scientists have discovered that the porous media can also be used for biomedical engineering and drugs delivery. So, for instance, in tissue engineering, porous surfactant can support cells growth and nutrient flow, while in drug delivery, porous material can regulate the release of medication over time. So, in our real life, the systems works much more complex than our expected. So, there's a new concept which is called poroelasticity, was proposed by a scientist whose name is Bott. So, poroelasticity is a field in material science and mechanics, uh, and that study the interacts between the fluid flow, pressure, and bulk solid deformation within a linear porous media. And it is extension of the elasticity and the porous medium flow, such as the diffusion equation, and which describe how fluid-filled porous material responds to mechanical force. So here's two formulas about the poroelastic, how the poroelastic contain with the stress-strain relationship and the stress-pressure relationship. So you can see that where H is the poroelastic constant and how it works in these formulas. So there's one more paper was selected to help us to go with a deeper research, which is called a thermopore-elastic model for flow transport in tumor tissue. So this paper introduced a thermopore-elastic model to study fluid transport within tumor tissue and incorporating thermal expansion and stress included deformation effect. So by modeling the tumor as a sphere, deformable porous media saturated with the interstitial flow pressure, which is called IFP. So the study explores how heat generated within a tissue impacts IFP and flow dynamics. So this paper using a finite element method. So the author solved the governing equation for temperature, displacement, and fluid flow to evaluate the influence of different heating conditions. So the paper's result shows that the temperature variation can alter pressure and velocity flow within the tissue and impact drug deliveries. So the study reveals that periodic heating creates the non-uniform pressure fields and potentially enhance the advantic transport. So a crucial factor for delivering macromolecular drugs within a low diffusivity into tumors. So this model contributes to understand the mechanism, effect, flow, and drugs transport in cancer therapy with an emphasis on hypothermatic effect. So after that, my teammate will explain more in detail of the physical meaning of this equation for the papers.
Hi, thank you for Jiaqi's introduction. I want to explain more details about the paper. Let's start at building the spherical tumor model. The left photo is the sketch of the model. ReV is representative elementary volume of the porous medium is defined as the volumetric average of the generic variable. The tumor is here assumed to be a spherical deformable porous media consisting of two phases. The solid phase is the extracellular space and the cells, and the fluid phase is the interstitial fluid. The tissue is assumed as a fluid, saturated, homogeneous, poroelastic medium. For the solid phase, in over several intercapillary distance, the domain is homogeneous and the capillaries are described as sink source points. This is mathematical formulas that describe the model we built before. Let me explain the physical meaning first, and then I will explain more about how to derive it. We can see the left-hand side is volumetric strain E evolution, and the right-hand side is the external driving forces. It's the general physical meaning, so let me go in deep. This part is the rate of change of volumetric strain over time. This is the diffusion term for volumetric strain, representing dispersion caused by elastic effects. This is the coupling term for volumetric strain in fluid flow, describing the effect of fluid compression on strain. On the right-hand side, this part is the coupling effect of pressure gradient and thermal expansion. This is the additional stress caused by thermal expansion, expressed through the temperature gradient. For deriving the final formula, we need these three equations first. The core of equation 2.11 is to describe the distribution of stress in tumor tissue caused by thermal expansion, elastic deformation, and pressure effects. The entire equation equals to 0 indicates that there are no additional external forces and the system reaches internal equilibrium. And this is mass conservation equation for fluids, describing the relationship between the accumulation, outflow, and generation of fluid. This is a volumetric source term describing the rate at which fluid is generated or removed within a unit volume. This is Darcy's laws, which describe the relationship between fluid velocity and the pressure gradient. My partner will explain more details about it later. Formula 2.11 under a spherical one-dimension reference system, it can be rewritten as formula 2.15. The generic solution of this ODE is this. Apply boundary condition on it, we can get C0 equals to 0, so we can get 2.17. And we also can rewrite 2.2, 2.4 under one-dimension spherical coordinate and combine with equation 2.17 to get the final equation 2.19. Equation 2.19 is a PDE in which the temperature appears in terms of the temperature difference. This means that the temperature field has to be solved at the same time. In spherical coordinates, we have this formula. In this equation, the second and the third term on the right-hand side and are heat generation due to metabolism and hyperthermia. After we derive all the formula we need to dimensionalize them. These are all dimensional variables are defined. We define, use these things, we can derive strain equation, pressure equation, velocity equation, and the energy equation. Then we define the initial and the boundary conditions to align with the simplified model, ensuring its relevance and the practicality in addressing the physical problem. Utilizing Cosmos multiple physics, we numerically solve the governing equations, carefully considering the interplay between thermal expansion, elastic deformation, and the fluid flow. Following this, we conduct an analysis of these results. However, to keep our decision focus, I will not dive into the details here. Now let's welcome Celine to share more about the Darcy laws I mentioned earlier.
Now you have some idea of the complexity to build a mathematical model for fluid flow in non-homogeneous and nonlinear poroelastic media. But how is it different from what we have learned so far in class? Let me show you some step-by-step comparison. Let's recall Darcy's law. Darcy's law is considered a continuum approach to model fluid through porous media. For a homogeneous and isotropic medium, Darcy's law is written as V equals to negative H del P, also known that H equals to the hydraulic conductivity K over mu, which equals to kappa. So equation can also be written as V equals to negative kappa del P, where kappa is the effective conductivity parameter. So this law states that the flow is proportional to the pressure gradient and is applicable in various types of fluid flow through porous media. It may not hold for non-Newtonian fluid and fluid with high velocities. I would like to focus on interstitial fluid flow, more specifically fluid flow through tumor. Darcy's law has been widely used for interstitial fluid due to its simplicity and empirical reliability. Now I would like to use one simple example to demonstrate the difference between solving it using Darcy's law and the nonlinear approach discussed in this paper. Consider this intratumoral infusion of a therapeutic agent into a spherical tumor. The goal is to determine the pressure and velocity profile of fluid transport under steady-state conditions. Say that the fluid is injected at the core of the tumor, and the boundary conditions are given as listed here. Pressure at both center and at the periphery are known. Some key assumptions are steady flow through a spherical tumor with unidirectional flow in R direction. There is no thermal effect and there is no source and sink. Starting with our approach 1, we'll be using Darcy's law to solve for a linear model. We know that Darcy's law is V equals to negative kappa dp dr. And our system has unidirectional flow in R direction, so the continuity equation simplifies to this listed. And integrate the continuity equation twice to obtain the general pressure profile. Then we plug in the boundary conditions to obtain pressure expression. Then we substitute pressure into Darcy's law to get our velocity profile. Clearly, this approach is quite easy and straightforward. Now let's look at our nonlinear approach. So our non-dimensionalized governing equations are listed here, which are also provided in the paper. Then we'll apply our assumptions that it's steady flow and no thermal effect. So we will be canceling out these 4 terms. Then the paper also gave us this correlation, which again, with no thermal effect, we'll obtain P star equals to E. Then we will substitute that into our simplified continuity equation to get the equation on the right side. Now, in order to solve this differential equation, we will split into homogeneous and particular solutions. Then we will obtain this equation. Next step is to apply the non-dimensionalized boundary conditions, plug in to solve our pressure profile, and switch back into the dimensional form. Then we'll get this expression. And also for velocity profile by solving this governing equation. And similarly, switch back to dimensional form to get this equation. So here are listed the pressure and velocity profiles we solved for each case. As shown by the name, Darcy's law gave rise to a linear proportional model, whereas the nonlinear model is impacted by beta exponentially. I would like to discuss 2 major differences, which are the beta and phi terms that only appears in the nonlinear model. So beta is a dimensionless parameter that indicates the resistance within the tissue matrix. The higher the beta value suggests a greater resistance to flow within the tumor tissue, which affects the fluid's ability to move through the porous structure. Another key difference between the 2 models is the effect of porosity on conductivity. Since mostly in linear model, the hydraulic conductivity is typically treated as a constant. But for nonlinear case, conductivity depends on both the porosity and the strain. If we make the assumption that the strain is small, since there is no drastic change in material structure or property, the relationship can be expressed as these 2 equations. Then we can see that when there is a higher strain, porosity would decrease, so as the conductivity. This indicates that there is more resistance to fluid flow due to tighter pore structures. Even with this simple problem, we can see that the nonlinear model is more complicated and requires more information to build the model, therefore makes it a more realistic model. That being said, Darcy's law is still a fundamental and practical choice for modeling interstitial fluid flow as it is simple, straightforward, and applicable generally. It does have its limitations, but it can be a great starting point for modeling fluid dynamics and can be modified and integrated into a more accurate model as we learn more about the system.